So I guess we'll start today's session. Just a second. So welcome everyone to the week 9 of this problem solving sessions for the course titled as Semiconductor Devices and Circuits, which is originally taught by Professor Sanjeev Sambandhan. And so I am taking this weekly classes on every Sunday from 7 to 9. And I am a PhD student at IIT Jodhpur, and I am working on this flexible and organic transistors, that is the OFETs or the OTFTs. And so this is my basic details and everything. So this was the basic course layout of this course. Up until now, we have completed more than half of the course, that is 8 weeks, and we have already learned about the basic device structures and everything. We have moved towards the transistors, that is the bipolar junction transistors. And now we have already learned about the MOS caps, that is the metal oxide semiconductor capacitors, or the MIS caps, that is the metal insulator semiconductor capacitors. So now our main focus moves towards the MOSFETs, the different characteristics of these MOSFETs. What are the various kind of a circuits we can like we can implement utilizing these MOSFETs, like singular MOSFETs, and also like with an array of these MOSFETs and everything. And the final thing would be the more research kind of a thing, that is the thin film transistors. So like I'm working on this field only now. So this week, throughout the lectures, what we have learned is the types of MOSFETs, which kind of a MOSFET has a different structure and those things, the IV characteristic of this MOSFET. There were several derivation of the equations, that the key parameters like the mobility, VTH, like that means the mobility for the for the channel mobility, and then channel thickness, and depending on the channel sizes, that is the width and the length, and there were like subthreshold slope, subthreshold swing, and this kind of parameters. So let's move on to the basic recap of the course. So I guess it's okay. So firstly, this week what we have learned is the structure called MOSFET. It's an exact similar structure to an MOSFET structure, that is the metal oxide semiconductor capacitor structure. But in this, what we have learned is that uh, this is like a slightly different kind of a structure. So let's first start with this. So if we have a sorry box kind of a structure like this. Now in this box, so like first we know that there are at least three terminals. So what we can make is that we can connect these three terminals differently. So the basic MOSFET structure had three terminals, and based on that we are just connecting three terminals like this. Now for a transistor, this thing is called the bulk or the base contact, and this is known as VB. VB for bulk and base both. Now these two terminals are very identical terminals, so they can interchange with each other. So I can just name it the source terminal and this as the drain terminal. The voltage is sorry, the voltage is VD or VS. Now, based on the device architecture, so if this total thing is a P-type semiconductor, we can dope this part and this part differently with the more N plus type impurities and N plus, like that is heavily doped N type impurities. And so this is a metal structure. This is a metal. This is also an metal contact. Now for this like above structure, what we are doing is that we are depositing an oxide layer that is working as the oxide, that is the MOS, the O in the MOS. So this is the structure here, and this structure is the oxide layer. And on top of that, there is the gate structure. So this is the gate, or the applied voltage is VG here. So this is a basic enhancement mode MOSFET. For different types of MOS, it will be changed with N type, whereas these parts will become P plus types. This one will be also P plus type. Apart from that, everything will remain same, and the selection of this contacts. So V, not V. So we can say the source and drain, both of these are completely interchangeable. So that's why it obviously needs to be identical as well. So they are completely identical, and based on the applied voltage there, we can change the nomenclature to VS or VD or those kind of a things. Now, so this one is the body is drain. Now, depending on the applied, just a second. Yes. So depending on the applied voltage between these two, so VGS, let's say, is defined by VG minus VS. Similarly, if we are applying a VDS, it is nothing but VD minus VS. So the applied voltage on the drain terminal with respect to the source terminal. So the difference is called the VDS, VGS and VBS. VBS is also same. So the applied voltage as the base or the bulk material with respect to the source. Now in most of the cases, this source is, I'll just use a different color for this. So this source is in most of the cases grounded. So based on this, we can say that as it becomes zero, so we can write VG for the VGS. Similarly, for this, we can write VD, and for this, we can write VB as well. So in several problems and in several areas where we don't define the VS, we had to assume that the source terminal is directly grounded based on a common grounded area. So all of the different voltages applied to them are with respect to a common ground, that is the source voltage. So now, and yes, so like to this is a very symmetric design. So this length, if I use this, so this length is very similar to this. This length is very similar to this. Similarly, in both the cases, if we are dividing it by half, both sides are identical to each other. That's it. And are there anything more? So yes, and so another part is like why the heavily doped regions. So there's a particular reason why this region, why this region and this region is heavily doped. So this is the basic reason. So the basic and primary reason is to avoid the contact resistance formation. So if we are just heavily doping this area, we'll get a very low contact resistance based area. And another part is like it also promotes tunneling, which is exactly similar to the contact resistance case, that because of there is a tunneling going on, there will be a very low contact resistance as well. But these are kind of a vice versa thing. And also another part is this the main factor is this area. So this metal semiconductor contact needs to be ohmic, right? But in reality it is not ohmic. This is an Schottky barrier, and although it looks like an ohmic structure, but this is an Schottky one, and because of that we need to reduce this contact resistance formulation. So and this is also to promote the tunneling as well, and that is why it is either N plus or an P plus region. Now apart from that, apart from that, we need to know several like key parameters for these things. So these parameters are the first of all the channel. What is the channel? So a channel is this area. So a basic thing, let me draw it again, I guess, so it will be better to understand. So if the structure is like this, let's say we have a gate here, we have a this kind of a structure, we have a this kind of a structure. These are our contacts. This is the oxide layer and this is the gate layer. We are applying Vg here. This is Vs, this is Vd, and this is Vb. Now there's a formation of a channel. So what is the basic assumption is that through this area there should be a basic current flow, right? Just a second. So through this area there should be a basic current flow. Now as in most of the cases this is a grounded one, so the current flow should be this way. Now to form this pathway, this is called the channel formation because this is a basic p-type region. So we need a formation of a pathway in this place that will promote this like current flow through this material. So this area is known as the channel. is the channel. Now we need to understand some basic parameters regarding this channel. So what is the different dimensions of a channel and those things. So the first parameter what we need to know is the channel width. So W. What is the channel width? So as like we are drawing it in a 2D format, but it's really in a 3D, like a 3D structure. So what will happen in this case is that, so if we are just drawing the channel, let's say the channel looks like this, right? Just remove it. The channel is like this. So channel is here, but the actual formation of the channel is like this. So obviously, as this is a 3D structure, it will have a height, it will have a width, and it will have a length. So apart from this, like channel width, there is another parameter that is the channel length or L. So both of these parameters, measuring both of these parameters is very important because they give us the factor called the aspect ratio of the channel. And it is very important to measure the other key parameters based on this. So aspect ratio is a very key like performance parameter. And so maybe I'll write the others here as well. So apart from this, there are there are other parameters as well. That is the capacitance density. So what is capacitance density? That is, normally we know that is Cox, but based on capacitance density or CI, but like Cox is the oxide capacitance. We know this, and we know the area. So based on like the divisible of like if we divide this with the channel area, we get the value of CI. Now Cox we know the value, and we can directly measure it from the CV characteristics. Another like a new factor that we get to know here is the overlap region and overlap capacitance. So previously we knew about the depletion region capacitance, that is the C depletion, and based on different interfaces creating different resistance type of a thing, we can term it as the C of the interface. But overlap region and the overlap capacitance is a different thing. So if we are just drawing this part, here we have the gate region. This is the gate. Here we have the oxide layer, and if we have the p-type regions like this. Now, so we can directly see that there is a basic overlap region forming here. Sorry. So this region is called the overlap region. So this region, so what is overlapping with the other parameters? So here, sorry. So the overlap region is that the gate and the source slash drain regions overlap here. So if we are just drawing this, let's say here in this case, so we can just basically term this as the source region. So this one is the source region, And if we can just term this as the drain region, so this is the drain region, this is the source region, and if there is a certain region, so if let's say this is the gate region and this is the gate region, so this total region is the gate region, right? So there's a certain overlap in both of the parts. So gate with the source and gate with the drain. These two regions are combinedly called the overlap region, and we have a specific capacitance based on this, which is the sorry. This capacitance is known as the C overlap, and the value of this is, so this is the basic value of C ox multiplied by the L overlap region, length of the overlap region with the width, because throughout the whole width the overlap region exists, but only at the length of this overlap. So here is half overlap and this is the half overlap. We are just summing both of them, so that will like come out as the L overlap, and this L overlap with the W multiplied with the C ox is the C overlap. Now we'll move to the next parameter. Apart from this, there were, I guess, just a second. Yes. So apart from this, the other parameters, before going to the other parameters, we also need to know the symbol of this MOSFETs. So a basic MOSFET is like this. So first we have the gate region here. There is the gate region. There's a separate region here. There's a separate region here, and there's a separate region here. So the first one we know is the source, as the source, and this one is connected. So this is source, as this one is the bulk. So the flow will be towards this, and this will be. So this is a very crude way to draw this, but this is the drain. So this is for a p-type one, obviously. Just a second, sorry. Just a second. Yeah. Yeah. Okay. So I guess I'm visible. Yes. So this is the symbol of a basic p-type enhancement type MOSFET. So to simplify this, if we know that like we can simplify it towards like this, we can draw it like this. So this is the gate region, but now we have only 2 points. So like if we are ignoring the bulk or the body region, we can draw it as S and this as D, and we just have to just put the arrow here. So in both the cases there will be a circle over this, so I'll draw the circle later. And even we can further simplify it as like this for the p-type cases and n-type cases. So this one will have, I guess, the dot. And this is the gate terminal, obviously. So all of this structure will also have this. So it will look something like this. And similarly for the, sorry, and similarly for the n-type cases, the easiest way to remember is that we'll just interchange the source terminal with the D terminal, that is the drain terminal. So we'll just change the nomenclature, and also we'll plus what do we need to do is to change the direction of the flow. So we'll also change the direction of the flow along with this. So if we are just drawing with this structure, let's say, so what will happen is that this will look like this. This will, oh sorry, this one is like this, not like this. If it looks like this will be the gate terminal. This will be the gate terminal. This will be the drain terminal. This will be the source terminal, and the flow will be towards like this. So this is for an n-type enhancement MOSFET. We just have to interchange the source with the drain terminal along with the change of the direction of the flow. Now, so we'll be moving towards the other key parameters. So other key parameters are the different voltages as we already saw. So the voltages applied. So these are the gate to source voltage and VDS or drain to source voltage. So as I have already discussed, that is the difference between the gate applied gate voltage with respect to the source voltage applied. In most of the cases, those are normally zero or they are grounded. Now, so and this is the E parameter here. Now, if we are moving towards the current voltage characteristic of these devices, this is very similar to the MOSCAP characteristics and everything. So what will happen if like in a structure like this, so in a case where the value of VGS is 0, so we are not applying any kind of a gate voltage along with the source which is grounded already. There won't be any kind of a flow, that is the value of IG, that the gate current is anyway 0, and with respect to that we can say that the input resistance is nearly infinite or like similarly like infinite. Let's say it's nearly infinite, and based on that, this means that no gate voltage is applied. So without the application of an gate voltage, without the application of an gate voltage, um, and so there's a infinite resistance in the input terminal, and based on this what we get is that we don't get a current at the drain terminal as well. So in this case, even if like let me write it, even if we know the source is grounded, right? Even if the D terminal or the drain terminal is positively, or is there's a positive voltage applied to it. Now what will happen is if we increase the gate voltage, so if we are increasing the gate voltage but still which is below the threshold voltage, what will happen is that there's a voltage flow but that is very low to start the operation. So this voltage is called the channel voltage. So the channel voltage or the VC, so there will be VC, but there will be no channel formation. To form the channel, so for this channel voltage to be formed, we need an increase in this value. So whenever we are giving a VGS greater than VTH, we have enough channels, we have enough VC, and the channel starts to form. In this case, we found a ID value, positive or negative. So we found an ID value, which is, if we divide it with the W and H, we know this as the current density, which is nothing but QNVD or QN mu epsilon. So this is the current density. This is also an important parameter to note down. So this will be parameter number F, current density. So whenever there is a much higher current than the threshold voltage, there will be an formation of the channel, that is the channel formation voltage or VC. Based on that, we get drain current, and based on that drain current we can calculate the current density, that is another key parameter. So that is QNVD or QN mu E. So apart from that, uh, we are not going into the derivations and everything of this thing, but we know that VDS is, sorry, I, I have to write like this. IDS is nothing but mu W by L C ox VGS minus VTH multiplied by VDS minus VDS by 2 whole square by 2. So this equation is valid only in the linear region. That means when VDS is less than VGS minus VTH. Now, similarly, for the saturation region, the equation will be changed and it will be IDS equals to mu by 2 multiplied by W by L C of VGS minus VTH whole square. So this is for the saturation region, which means VDS is greater than or equals to VGS minus VTH. Now, at what will happen at VDS when VDS is equals to VGS minus VTH, we'll discuss it. But so this is the basic saturation condition, and this is the basic linear condition. To work the device in a linear region, the current will flow like this, and to work the device in saturation region, the current will follow this equation. Now, there is another key parameter that is known as the phenomena called as the pinch off, or the thing we need to know more is the pinch off voltage. So what is a pinch off voltage? So when the value of this thing VDS uh, is greater than or equals to the value of VGS minus VTH, what happens is that the region near the drain where the channel uh, the channel starts of getting pinched off. So like starts getting pinched off, that is it can't exist there. So this looks like something like this. So if this is the source terminal and this is the drain terminal, the top gate is here, and based on this, this is the region, channel region. So this is the channel. So what will happen is that there's a certain phenomena called the pinch off. So what will happen is that the channel is getting diminished by this structure, and this is called as the pinch off. Now, so this means also that it is already doing this thing in saturation region, obviously. So saturation region is also another region in which that even if you increase the amount of VDS, so this saturation region is completely independent of this VDS, obviously, because even if we are increasing the VDS, there is no further increase of the current or IDS. So even if the VDS is getting increased, there is no further increase in the IDS value. So we can say this. So this is completely independent of the VDS, the channel formation. So at a certain voltage, that is the VP or the pinch off voltage, this is at a point where the voltage is like pinched off. So this voltage is called as the pinch off voltage, and this is also another very important parameter. After that, we need to know that, like, as we have already assumed that there is no connection between the saturation region current and also the VDS. So we have to, oh, sorry, we have to say this as the, so saturation. So IDS in saturation, or we can write it as IDS sat, let's say, for the time being. So this IDS sat is completely independent of the value of VDS here. But in reality, what happens is that if we uh, will like decide the name further, but if we keep on increasing this VDS, if is increased further, what will happen is that the pinch off point, so the pinch off point is at this point. So this is the pinch off point. This pinch off point shifts towards the source terminal. So the pinch off starts shifting, and it will look something like this. So if the pinch off was like this, it have already shifted like this. So now the pinch off point is here, whereas it was here. So it is moving towards the source terminal, and based on this, the effective channel length is decreased, right? Is decreased. So this phenomena, the effective channel length is getting decreased with the further increase in VDS, is called as the channel length modulation. So similar to the, like in BJTs we have the, in BJT we had the base width modulation, right? So similarly in this case we have a channel length modulation. What happens is that if we keep on increasing the VDS, the channel length, the pinch off point shifts towards the source terminal, and because of that, what happens is that, which is like as per our assumption, it should be independent. So there shouldn't be any increase or decrease in the IDS value with respect to the VDS, but still based on this VDS, the pinch off point shifts, and this is called the channel length modulation, and the channel is getting decreased. So based on this, we have to modify the IDS equation in saturation regime, and it will have a factor that is lambda VDS. So we have to multiply a factor, and the new equation will look like something like this: IDS equals to mu by 2 W by L C ox VGS minus VTH whole square, but it will be also be 1 plus lambda VDS. So in the first case, like if the equation was like this, based on this, we had assumed that there is complete independence from the VDS value, but based on this channel length modulation case, we have to include a factor that is dependent on the VDS. Okay, now if we are moving towards the like the different kind of a characteristics for this like devices. So the first key characteristic is the transfer characteristics. So what is the transfer characteristics? Transfer characteristics looks like this. And if this is the IDS value with respect to the, just a second, sorry, with respect to the gate to source voltage, the IDS value looks something like this. These values keeps on increasing, and for different values of VDS, the value keeps on changing. These will, let's say, like this. We have to remove this. Right. Okay. So these values will look like something like this. So this is called as the transfer characteristics, and based on these values are based on different amounts of VDS value. So if this is for VDS1, this is for VDS2, and this is for VDS3. Okay. Now, similarly, there's another characteristics that is known as the output characteristics, which will look like something like this. Another thing is that, no, let me first do this. So, apart from output, what we can do is that we can also plot this transfer in semi-log axis. So, what will happen in this case is that it will anyways be VGS, but it will be log of IDS. The plots will look something like this, not exactly like this. So they will start off a bit late, and based on different values of this, it will have different values. Okay, so with VDS1 and VDS2, it will be different. They will be slightly different, but that's fine. So we can also plot this transfer in semi-log axis as well. And what is the reason of that? We'll discuss later. But apart from that, there is another characteristics that is the output characteristics. So the output characteristics is the variation of IDS, but with respect to VDS. So the output current, that is the IDS current, is varied with different values of VDS. What will happen if we are just sweeping the value of VGS? It will look something like this. Now, here, let's say this is for VGS1, this is for VGS2, and this is for VGS3. So there will be a certain region where the value is getting linearly, kind of a linearly increase. So this is the linear region, and here the values are kind of a saturated. So this one is called the saturation region. Okay. So this is the saturation region and this is the linear region. I'm sorry. Yeah, it's visible now. Now, so here's a little bit increase in this values even after like the device is under saturation region, and this is because of this change in VDS values, not in the VGS values. So this is for the term, new term we have included in this, that is the channel length modulation. So this further increase in the IDS values is because of the channel length modulation, that is due to the term that was 1 plus lambda VDS. We have previously included in the equation. Now, there's a certain region called the, let's move to this page and we'll go back to the images there. Now, so there's a certain region called the subthreshold region. So what is the subthreshold region? A subthreshold region is a region where the value of VGS is less than VTH. So it is not obviously in the threshold region. So what will happen is that there will be a very small amount of current present in this case, and which is due to more carrier near the source terminal. So there will be a certain accumulation of carriers near the source terminal, which is directly due to the carrier diffusion. So due to the presence of diffusion, yes. So due to this presence of diffusion, what will happen is that more charge carriers will be present at the source terminal, near the source terminal, and based on that, there will be a very small amount of current present, even if the gate voltage is not exactly at the VTH or even higher than the VTH. There will be a certain amount of low amount of current, and this region is called the subthreshold region. So now at this subthreshold region, we have few important parameters. So the last parameter what we have learned was current density, right? So the next parameter we need to understand is the subthreshold swing, or the SS. So how to calculate this subthreshold swing? It is nothing but the change in VGS. So how much the VGS changes with respect to a decade change in the current. So it can be directly calculated from the transfer characteristics as well, or we can write it as ln of 10 dVGS by d psi s by d of ln of IDS, or we can write it as ln of 10 kT by Q, that is the thermal voltage, with 1 plus C depletion with the C interface divided by C aux. So this is the value of SS, and how to determine these values are that through directly from the plots we have got from the device itself. So if we are plotting this thing, so as we know that we need a decay change in the idea, so it is very easier to do it on the semi-log scale. What is here is that if this is, let's say, here, from here we can directly determine any decade change. So let's say if from here to here it is a decade change or 10 times change. Based on this change, and based on this change we can get the corresponding change in these values, right? So we can get this value of the VGS change. So based on the definition of SS, it is the change in VGS with respect to 10 times change in the IDS values, right? So as we can directly get the decade value change in the IDS values, we can just plot them back to the VGS change. So this value is called the SS. So we can directly get these values from here. Similarly, with respect to this, what we can do is that we can, just a second, yes. We can also plot this thing. We can also plot another curve that is noted as the root IDS versus VGS curve. This is nothing but the we are just getting the square root of this axis from the transfer curve, and if we are just plotting this, so this will look like this. This is VGS, this is IDS whole to the power half. If we are plotting this, we'll get a figure something like this. And if we are just extrapolating this value, if we are just extrapolating this value, we can directly get the value of VTH from here. So directly from the plot itself, if we are fabricating a device or something, we can directly get the value of VTH directly from the slope of this root over IDS curve. We can get the value of subthreshold slope from this. And oh, also sorry, I forgot to mention that, is that from this, if we are just reciprocating this SS value, we can also get the subthreshold slope. So this is the reciprocal of SS. So if we are just reciprocating the value of, if we are just inversing the value of the subthreshold swing, we can directly get the value of subthreshold slope, and which can be directly determined from the curve itself. From the curve itself, we can also get the value of VTH. If we can measure the value of W and L, which is already fixed for the device fabrication, we can directly also get the value of mobility as well. So mobility can be determined because from the device fabrication we already know the value of COX, we already know the value of VTH from this kind of a structure. So from this plot we can already get that we already have the value of this subthreshold swing, and for this, and also we know the aspect ratio as well. Based on our design constraints and everything, we can directly get the value of W by L, and from that we can directly measure or determine the value of mobility here as well. So for a certain device, if we can get the output and the output of the transfer characteristics, and based on different functions of that transfer characteristic, like the logarithmic or the semi, if we plot that in a semi log axis, or if we plot that in a root over kind of a way, what we get is that we can determine all the values from here directly without even having a direct in-depth knowledge of the device itself. So we can get the value of threshold voltage, we can get the value of COX, we can get the value of this thing called the aspect ratio, we can get the subthreshold swing, and we can get the mobility as well. So this was the basic thing we have learned this week. So if anyone have any question, you can ask me right now, or otherwise we'll move to the questions and those things. Anyone have any questions? Sorry. Based on the structures or anything. So if there are no questions, we can start on the problems. So question number one for today is that we'll have like a small number of questions today because these things are more to be learned from the device fabrication and the in-depth of the device rather than the problem solving, but still we have to figure out the values of this threshold voltage, the mobilities and those things. So we'll have a small number of problems, but take a bit time and try to solve the questions by sorry, try to solve the questions, sorry. Now so let's consider n channel MOSFET with a W of 15 micron and L of 2 micron and Cox of 69 nanofarad per centimeter square. So we right now have the aspect ratio and also the Cox value. So if we want to calculate the mobility, it will be much easier for this case. Right now, assume that in the non-saturation regime with VDS of zero point 0.1 volt, the drain current is 35 microamperes for a VGS of 1.5 volt and 75 microampere for a VGS of 2.5 volt. Now, so what we have is that in the non-saturation regime, so it can be in a linear regime. Let's guess that it's a linear regime. So what we have is that the drain current is 35 microamperes when the VGS is set at 1.5 volts, and the drain current is 75 amperes microamperes for a VGS of 2.5 volts. Now we need to find the compute the threshold voltage of the MOS. So we need to find the threshold voltage of this MOSFET. Now to sorry, this just a second. Okay. So I'll just like go through the problem again. So we have W, that is 15 micrometers, L. So we can directly get the aspect ratio, that is W by L. We also have the value of Cox, that is 69 nanofarad per centimeter square. So it's better to convert everything into centimeters. Now what we have is that for the VDS is set at 0.1 volts. Now what we have is that when the VGS is 1.5 volt, the drain current, that IDS, is 35 microamperes. When the drain current is VGS of 2.5 volt, the value of IDS is 75 microamperes. So it's a very easy solution. Try to solve this. Take 5 minutes or so and try to solve this. So it's if anyone has not been able to solve this, let me solve this then. So what we know from this problem is that we have two different cases, right? So we'll have to solve this in two steps. So we have case 1 and case 2. So for case 1, what we have is that, so first of all, what we need to know is that this value of this VDS is very, very small. So as this is very small value, what we can do is that, so first of all, we know that the value of ID is nothing but mobility Cox W by L VGS minus VTH multiplied by VDS minus VDS square by 2. Now, as this value is very small, the square of this thing will be very, very small. So for these cases, what we can do is that we can omit this part. We can just neglect this part. Not exactly 0, we can neglect this part. Now, for this case, what will happen is that the value of this ID will be mobility Cox W by L. So we know the value of W by L, that is the aspect ratio. We know the value. We know the value of Cox. We know the value of ID in this case. So what we can do is we can write it as the ID1, that is the ID for the case 1. And similarly, what we can do here is that we know the VGS value. So we can write it as the VGS1 minus VTH, which will remain constant for both the sides, and VDS for both the cases, as VDS is common for both the cases. Similarly, here we can write the identical equation, but it will be like this: ID2 Cox W by L. This will be VGS2 minus VTH multiplied by VDS. Now, the best option is to just to divide both the parts. So if we are just dividing this, VD ID1 by ID2 equals to mobility Cox W by L divided by mobility Cox W by L. So we can directly know that we can just cancel this total term out, or we can cancel it like this. Sorry. So what we can do is that VGS1 minus VTH multiplied by VDS by VGS2 minus VTH into VDS. So we can cancel this VDS out. We can cancel this mobility out. We can cancel this Cox out and W by L as well. So based on this, we can just write the equation easily. That is ID1 multiplied by VGS2 minus ID1 into VTH is equals to nothing but ID2 into VGS2 minus ID2 into VTH. Now, if we are just writing this, so just a second. So it will be ID1 minus ID2 multiplied by VTH is equals to um, ID2, right? This one is this, sorry, ID1 minus ID2 multiplied by VG. Sorry, just a second. So this one VGS, ID1 will be VGS2 and ID2. Sorry, this one will be VGS1. So we can't take this. So it will be ID1 multiplied by VGS2 minus ID2 multiplied by VGS1. So we'll just put the values in the next page. So this will be nothing but ID1 minus ID2. So that will be ID1 was how much? ID1 was 35 minus 75 microamperes multiplied by VTH. VTH equals to ID1, that is 35 multiplied by VGS2. VGS2 was 2.5 minus 75 multiplied by 1.5, and the value of VTH is nothing but 35 multiplied by 2.5 minus 75 multiplied by 1.5 divided by 35 minus 75. We just have to put the values and this will be in volts. Just a second, let me put the values here. That is 35 2.5. So 35 multiplied by 2.5 minus 75 multiplied by 1.5. So the top part comes out to be minus 25 divided by minus 40. The value is 40. This is 0.625 volts. So the threshold voltage is 0.625 volts. So what we have done is that we have just taken a consideration that because VDS is very small, so if we were calculating VDS squared, that will be very small, right? So that would have been 0.01 divided by 2. So that would have been 0.005. So we have just omitted that part. And because of that, what we have got is that we have easily calculated each of the parts and we have just got an very smooth equation of like this: ID1 minus ID2 into VTH, which is equals to ID1 into VGS2 minus ID2 into VGS1, and we have got the value of VTH as 0.625. Okay, so if anyone have any question, you can ask me, or else we can move to the next problem. So I'll keep on writing. If anyone have any question, you can ask me. Okay, so the parameters of a p channel MOSFET are mobility of holes as 310 centimeter square per volt second. The T of the oxide thickness is 22 nanometers. The aspect ratio is 60 and the threshold voltage or the VTH is minus zero point 0.4 volts. Now, if the transistor is biased in saturation region, it does find the ratio of drain currents. So it is an exact similar problem to the previous one, corresponding to V VSG1, which is 1 volts, and VSG2 as 2 volts. So we have to find out the value of VSG1 and VSG2. VSG1, VSG2, we have the values. We also have the, let me write it down then, in this case as well. So what we have is that we have the mobility of holes, mu p as 310 centimeter square per volt second. We also have the value of T ox, which is 22 nanometers. We have the aspect ratio as 60. We have the threshold voltage, just remove it, just VTH as minus 0.4 volts. Now we have to find out the ratio of the drain currents when VSG1 is 1 volt or VGS is minus 1 volts and VSG2 is 2 volts or the opposite, so minus 2 volts. We have to just find out the exact same ratio what we have been working in the previous one, that was ID1 and ID2, and we have to just put the values here. So let's take 5 minutes and try to solve this. It's also an easy one. Uh, I'll just write out the equation, I guess. So for this case, they have already mentioned that this device is working in the saturation region, right? So for the saturation region, the value of ID sat is nothing but half of mu p Cox W by L V of Sg plus VTH whole square. So this is the value of basic this, and you have to just find it out. That's it. So in this case as well, we have to consider like two cases, right? So the case one and case two. In both the cases, we have to just put the values here. So ID sat one.
Sir, in ID set in equation VSG minus VTH, na? Yeah, or plus.
No, no, this is plus because the basic equation was what? Like the basic equation was VGS minus VTH, right?
Yes, yes, sir.
So that's why if we are just reversing it, it will look like
Okay,
this.
okay. In place of
And
VGS, right here,
and then minus
VSG.
of 1 whole square will become 1, right? So that's
Okay,
why
sir.
we can write it as like this. Okay? Yes, so for this
Yes.
case, what will happen is that half of mu p Cox W by L, and we have to just put the values of VSG and VTH. That's it. So for this case, it was, I guess we should have put this, but that's fine. So it will be 1 of minus 0.4. So ideally in like physical cases, what we do is that we write the VGS, and for the P type MOS, the values would be negative. So it will be minus 1, minus 2 like this. And for N type MOS, it will be positive. That's it. So for physical cases, we don't like determine these kind of a things, but for like mathematical problems and these things, you can write it like this: SG plus VTH or VGS minus VTH whole square. You can use both of them and it will like be same. And so this will be like this, and this is 2 minus zero point 0.4 whole square. Just we have to just ratio it. So do it and like take a minute and try to like, get the answer. Give me the answer. So it is 0.1406. Let's put the values then. So if we are just dividing both, so this sat 1 divided by ID sat 2. What will the value? So half mu p Cox WL, everything will get eliminated. So it will be zero point 0.6 square by 1.6 whole square. So let me put the values and recheck the answers. Zero point 0.6 square. Sorry, zero point 0.6 squared divided by 1.6 squared. So it is 0. Yes, yours is the correct one. 140625. For making it easy, you can write it like this, but the total answer is this. So this is the correct answer. So we'll move to the next one, that is question number 3. So what we have is a silicon n type MOSFET which has a W of, just a second, sorry, which has a W of 10 microns, L of 1 micron. The oxide thickness or the TOX is 20 nanometers, and the threshold voltage is 1 volts. 1 volts. The device is biased with a gate to source voltage of 3 volts and a drain to source voltage of 5 volts. Okay, assume that mobility is 300 centimeter square per volt second. The MOSFET is biased in which region? So we need to find the operating region. Also calculate the value of transconductance. So till now I haven't discussed about the transconductance. So for the time being, just like if you can do it, you try to do it. Otherwise, like I'll do that part. Or maybe I can give some this. So a transconductance is Gm, which is the variation of ID with respect to VGS. So how to do this? It is nothing but hmm, just a second. So this is nothing but the value of. So from here we can directly get the del ID by VGS. So we have this ID by VGS curve, that is the transfer curve, and the slope of this transfer curve is exactly the value of transconductance. So just put the values here and you can get the values, and try to find out in which region the device is working. Take 3-4 minutes and try to solve this.
So reason is saturation.
Yep. Yeah, that's correct. How did you solve this?
So because VDS is greater than VGS minus VTH,
Yes,
because
exactly.
VGS is 3 and VTH is 1.
Yeah, 2.
Yes.
Yeah, perfect. And can you calculate this transconductance? So I'll then do the first part for everyone. So here we know that VGS value is 3 volts and VTH is 1 volt. So the value of VGS minus VTH, as C already like discussed, so this is 2 volts, right? And from this as well, we know that the drain to source voltage is 5 volt. So we can definitely say that VDS is greater than VGS minus VTH. So the mode is saturation mode, or this transistor is working in saturation region. And now try to find out the value of transconductance. So the best option to do is that you have to just differentiate the equation of current. That's it. So del ID you can do from that, del ID by del VG, and you can get the value of transconductance from there. Then take a minute or two. It will take a minute or two, I guess. So I'll maybe solve this. So as we know that the region of operation is saturation, so we can directly use the saturation region equation, right? So IDS is nothing but mobility by 2 C of W by L VGS minus VTH whole square. We'll just divide it. So root IDS by del VGS. The value is mobility by 2 multiplied by 2 C of W by L VGS minus VTH. So we can directly just put the values. So mobility, this 2 will cancel out. Mobility was how much? Oh, so mobility was 300 centimeter squared volt per second. We need to find out the value of Cox. Cox is nothing but epsilon ox by Tox. So from here we can get the value of 3.9 because this is a silicon one, and 8.854 multiplied by 10 to the power minus 14 whole divided by 20 10 to the power minus 7. So why this is 10 to the power minus 7? Because this should be, everything should be in centimeter, right? Because other parameters are in centimeter. So W by L we have to convert it, but as we are just dividing it, we don't need to consider the micron. So that's why it is 10 by 1 multiplied by 2. So let's move it to the next one. So the left hand side is nothing but GM. The value is 300 multiplied by 20 multiplied by 3.9 multiplied by 8.854 into 10 to the power minus 14 by 20 multiplied by 10 to the minus 7. So this 20 comes out. This is 3 into 10 to the power of 2 multiplied by 3.9, 8.854 into 10 to the minus 7. So the final value is 3 multiplied by 3.9, 8.854 multiplied by 10 to the minus of 5. Let's put the values in the calculator and we'll get 3 multiplied by 3.9, 3 multiplied by 3.9 multiplied with 8.854. So this is nothing but 103.59 multiplied with 10 to the minus 5. This will be in Siemens. So this is 1.036 into 10 to the minus 3. We can just convert it to Siemens, I guess. Siemens, and this is 0.036 millisiemens. So the value of transconductance is this. So this is it. Anyone have any question? We are just defining this, and also to just to tell you this that trans. Yes, anyone?
Sir, how to find out the value of COX?
COX is we know, right? COX is epsilon ox by Tox. Epsilon of the oxide into Tox. Now epsilon ox is what? It is nothing but epsilon r into epsilon naught divided by T naught. Now epsilon r, as we have already known that this is a silicon in MOSFET. So epsilon r is nothing but 3.9, and epsilon naught we know the value, that is 8.854 into 10 to the minus 14, and Tox we already got this from this like question, that was 20 nanometers. So we have just directly put this value. Is it okay?
Okay, sir. Okay, yes, thank you.
Yeah. So what I was telling is that transconductance is also another key parameter. So actually I have omitted it because like it was not mentioned in the lectures. Maybe like in the next week it will be there or something. I don't know exactly for the time. But transconductance is a very key parameter, and there is something also called the process transconductance as well, which just considers the Ci, that is the capacitance density multiplied with the mobility. That's it. So this term, this VGS minus VTS term, we tend to omit this. So in that case, what happens is that we get the value called the process transconductance, and this is the basic transconductance for a device performing like this. Okay. So, with this, we'll end today's session. And I guess I have kept a very small number of questions, because in most of the books and everything, they had like a very similar patterned questions, and most of the questions are nothing but they are just changing the values and those kind of a things. So most of the problems are very similar to these kinds of things, that you need to understand what's the ratio of this current or the ratio of this voltage, how to calculate threshold voltage, how to calculate the aspect ratio, that is W by L, or something like this, how to calculate the transconductance, which region is it working, and what is the value of VTH, and these kind of like questions are very similar to this. So we'll end today's session with this thing, and in the next session we'll also learn more about this MOSFETs, and we'll have some more problems how to solve this MOSFET parameters, but based on different channel modulations and everything. So there will be different key parameter modulations, and how these modulations will affect the previously derived key parameters, that is the mobility, VTH, transconductance, the subthreshold swing, and those kind of things. Okay. Thank you for attending today's session. Thank you.